So welcome to the second part of this lecture or presentation on UV measurements. In the first part, I gave you a brief introduction into the way you can calculate and characterize your instrument. In the second part, I will go slightly more into the details. I will give you a first part which will be a bit more detailed on lamp calibrations. Some of you, I would say half of you, were doing the lamp calibration outside with the brewer. I will give you a little bit of background information on how you should handle lamps and what you should consider when you do a lamp calibration. And the second part of the lecture will be on quality control procedures, on how you could validate and check your measurements and compare them to other instruments. So to start with, I have put up a slide which describes the traceability chain of your reference for solar irradiance, where actually you are getting your lamp certificate from. And this slide actually illustrates how the uncertainties that you have from your lamp actually come from, and what the ultimate uncertainty is that you can achieve with your instrument. So on the top left corner, you see the absolute reference. That is the 0.01% uncertainty from a cryogenic radiometer, which is the absolute instrument that allows you to have irradiance value without any calibration. It's an absolute instrument, and that is forming the basis of all the irradiance scales that we have. And this is brought down step by step all the way to the black body, which forms the reference for spectral irradiance. At this stage, we have gone from a 0.01% uncertainty to about a 0.5% uncertainty. And this is all happening in national metrology institutes. So that's not something you are doing in your own home laboratory, but this is something that is done by very specialized laboratories, a few of them in the world. And these laboratories, in turn, they will calibrate lamps that then you yourself can buy and bring to your home institute to perform your own calibration. And this is what you can see on the top right corner, called the transfer standard. So these are those 1,000-watt lamps that we are having in our own laboratories, usually 1 or 2, and that form for us our reference. Now for us in the brewer world, we have the problem that the lamps that you get from these national metrology institutes, they are measured on a horizontal orientation, on a horizontal alignment. And the brewer that is always looking up to the vertical will also need to have a lamp that is operated that way. And now this sounds very academic, but it is actually a problem, because if you take a lamp and you change its orientation, then the output of this lamp might not be the same. So if you take, for example, this transfer standard, this one here, and you put it horizontal, then the output might change by 10 to 15%. So you really have to operate it the way that it has been used and calibrated. And so that means that for us brewers, we have this additional step that we need to go from this horizontal beam transfer to a vertical beam transfer, which we realize with the DXW lamp. All of that is happening in the laboratory, and now our instrument should be used outside in the sun. And so for that reason, we are all using small little lamp systems, like the 50-watt lamps that half of you have been using this afternoon, and the other half will be using it right after this presentation, to be able to calibrate your instrument outside where it is measuring. And typically at this stage, the measurements that you will be performing with your instrument will have an uncertainty of the order of 5 to 10%. This is an example that shows you how you actually go from a transfer standard that was calibrated by a metrology laboratory here to the vertical beams orientation that is required by the brewer. This type of transfer is being done with an instrument that has an optical fiber. You can see here the optical fiber and here the entrance optic of this instrument, because the optical fiber allows you to manipulate the entrance optic to different orientations without affecting its throughput. I'm not sure if any one of you have actually tried to orient the Brewer sideways. You can imagine that this doesn't really work. So you need some sort of different setup for that. So this is just an example of how a responsivity will look like if you measure a lamp with your Brewer. This is an example of a double Brewer, 163, that's mine. You will see here about 10,000 photons per second for 1 milliwatt per square meter and nanometer of radiation. You see the noise that I have had with this instrument when it was calibrated. These are 2 scans, one after the other. So the peaks that you can see, they are random. They are different in the red and the blue scale. You see here a sharp jump. That's the switch from slit 1 to slit 5. When you take the ratio, then actually it doesn't look that bad. You see that the 2 scans differ by about 1%. Now it's really up to you to know if that is good enough or if you want to achieve more. If you want to achieve more, then what can you do to reduce the noise? We discussed it just before. You have to increase the number of photons that you are measuring. So you have to integrate much, much longer, maybe 10 times longer, to reduce the noise by a factor of 3. Remember that it all goes with the square root. And now we come to the field calibration, the 50-watt lamps. On the picture, it's actually a setup for a 250-watt lamp system. You see that the lamp is not right over the diffuser, but there is about 25 or 30 centimeters distance between the two. The reason for that is because that way the diffuser on the Brewer doesn't get that much heat. The other reason is that the distance is very crucial in these calibrations. I'm not sure if you have that in your exercise, but if you change the distance by 1 millimeter, then the effect on the irradiance goes with the square of the distance. So if you have 1 millimeter out of 5 centimeters, it makes a different difference than if you have 1 millimeter out of 300 millimeters. That's the reason for having a longer distance between a lamp and your diffuser. Now these lamps, they are not calibrated themselves by having a calibration certificate, but what happens is that these lamps are calibrated in your laboratory relative to the 1,000-watt lamps that each of you should have in your laboratory. Because you cannot really make this type of setup with this relative distance and this setup that is very individual to your own instrument and get a certificate from that from an independent laboratory. You have to do that yourself. For example, half of you have done the lamp calibration, and the company was really careful in adjusting or having you adjust the voltage for 12 volt, 0.000. And this is because the output of such a lamp is very sensitive to the power that it has. Now, usually when we operate lamps, we are controlling the current and not the voltage. Now, in the case of the 50-watt lamps, historically, it was much easier to adjust the voltage than trying to adjust the current. But basically, it comes down to the same thing. You are trying to keep constant power on the lamp. And as you can see on this slide, the sensitivity of the lamp output to a change in power or current is really not linear. A 1% change in the current will affect your irradiance by 10%. So it's really crucial that the voltage or the current is stable to a very high degree so that you don't have your output of your lamp changing too much. So typically what you want to achieve is 0.1% stability in your power. so that you have a 1% stability in irradiance. Let's summarize. For lamp calibrations, just what we were talking about, you should have the power of your lamp really stable, because the output goes 10 times with the variability of the current or voltage. The distance is really crucial, that it is stable. It goes with the square of the distance. Here you have actually the solution. 1 millimeter out of 500 millimeters produces 0.5% variability. So if you have 50 millimeters, then it's 4%. And the 50-watt lamps, they are only calibrated relative to these 1,000-watt calibrations. And it's really up to yourself how often you want to calibrate it. I have given here rules, just typical values, once a month, once a week. It's really up to yourself to know how often you want to calibrate your instrument. Okay, I'm switching to the second topic. It's the quality control and the quality assurance that you can apply to your measurements and to your instrument to try to estimate the reliability of your measurements. I will just mention briefly comparisons to broadband radiometers. Half of you have been doing that in the practical exercise. You can compare your data to model calculations, you can compare it to satellites, and you can compare it to another instrument. That's the final part of the talk. So when you are comparing it to a broadband radiometer that probably everyone has sitting somewhere on its measurement platform, then typically we all have something that then finally gives an erythemal weighted irradiance, and you see here how you can produce that from your solar spectrum. You integrate it with the broadband weighting function, let's say the erythema, and you will get the erythemal weighted irradiance. But do not forget this little delta A here. Unfortunately, a single brewer only measures up to 325 nanometers, and a double brewer only to 363 nanometers, and you're missing some part of the solar spectrum. And if you do this comparison, then it's really crucial that you are comparing the same stuff, and your broadband meter really measures or gives you a value that goes all the way to 400 nanometers. And if you just integrate your solar spectrum from your brewer, and you don't think about this small little extra part, then your comparison will be biased. And I don't have the numbers with me, but I think if a double brewer misses this delta A, then you're off by 8%, and if you're missing it in a single brewer, then you're off by, I don't know, 50% or more. So this delta A is something you have to think of, and the problem is you are not measuring it. So one possibility is model calculations. Another possibility is just to go through the brewer operational software, and you will find out how they have been doing it. Your brewer UV spectrum or the UV routine solves that problem for you. This is an example of a comparison that we do ourselves. This is just a copy of our website in Davos, where we compare our brewer with the different broadband instruments we have on the roof. On the top left corner, you'll see two graphs, the red and the blue. The blue is the broadband radiometer, and the red is the brewer, integrated for erythema. From that plot that is in real time, you can easily see if the instruments agree more or less, or if they are far apart. On the bottom graph, you see number of dots. What they show is the ratio between the broadband instruments and the brewer for 2 days, one time against time, and the two right graphs against solar zenith angle. What you see is that actually the instruments are different. They are showing different behavior over time, over solar zenith angle. So that gives you an idea how well you can compare these instruments. I would say to within 5 to 10%. You have individual variabilities over time. You see, for example, on this figure, that this instrument is showing a funny shape over time, that when you look here, it's a sort of dependence with solar zenith angle. It's probably the limit of what you can achieve with these type of comparisons. 5–10%. This is a comparison that I got from Natalia Kuremetti. Comparison between models and satellites. And remember that this is clear sky. It's nearly impossible to make comparisons on the all sky situations where you have clouds, variabilities that you cannot model independently in your radiative transfer model. So for a good comparison and validation of your measurements, you need to constrain your data to clear sky, which for some stations might be really difficult. But now let's say we have a site. Here you have 3 sites, El Arenocillo, Thessaloniki, and Rome, for different wavelengths over solar zenith angle. So it's not an individual day, it's a summary of a huge amount of data. And what you can see are, for example, the black dots, which come from the OMI satellite, the UV product that you can download from their website. You see that it's off by 40%. And then maybe 20% around 320 nanometers. But there's a huge bias with the satellite. If you do a very good job with your radiative transfer modeling yourself, and you have as input the aerosol that you get from a co-located instrument or maybe from another satellite, then you can get better agreement, as you can see, for example, on these light blue curves where you are around 1 or within 5 or 10%. But it really depends on what type of information you have that you can feed into your radiative transfer model. And if you look at the one in Rome, for example, then you can see that over the course of a day, there are systematic dependencies with solar zenith angle of the order of 10 to 20%. So when we go back to our single instrument and we want to be independent of everything else and we want just to take that instrument, then there's not that much that we can do. But one thing that certainly can be done is that we can play with its own data, and something that has been done very nicely and where we have products that everyone can use is, for example, checking the wavelength alignment of the spectra that you are measuring. The advantage that we have nowadays is that we have high-resolution reference spectra that are very accurate in wavelength, and we can use them to compare our measured spectra with this reference spectrum. And this method is really very powerful because you can detect a few hundredths, or better than a hundredth of a nanometer shift between your instrument and this reference spectrum. I will not go into the details of how it's done, but you can see here 2 graphs. And on the left one, I plotted one measurement of, in this case, our double brewer, and it's divided by a lot of shifted high-resolution spectra. And you see that there is a lot of spectral noise in these ratios. And if I pick one wavelength, 317 here, and I plot it against the applied wavelength shift, then you can see that there's a very clear minimum where the residual are minimum. And this minimum means that at this place, both spectra agree the best. And that tells me that the best agreement between my reference spectrum and my measured solar spectrum at 317 nanometer requires a shift of 0.015 nanometer. And this can be done, of course, spectrally. And here you have 2 examples. You have an example for a brewer, where you can see that this wavelength shift over its own spectrum is not constant, but it actually varies. And you can see some funny shapes in the long part of the spectrum. On the right, you see a spectrum from a single brewer that extends only to 315 nanometers. It looks nice, but then maybe you want to check the scale. It actually has an offset of 1/10 of a nanometer. That's quite big if you consider that when you do your dispersion analysis, then the results of that are usually within 100ths of a nanometer. So clearly here something happened with this instrument that it's using its wrong dispersion. There are 2 softwares now available for that. The standard one, chic program from Harry Slaper, is available online. You can download it and apply it to your data. It's really quite easy to use and gives you exactly the figures that you see below. We have developed another one based on MATLAB, and it is available. I haven't yet put it on our website, but it is also available. It produces similar results, and it's open source and produces the same results. It is the same concept. It's not the same algorithm because I have invented my own. But the results are the same. I have validated it when I compared it with SCHC. It gives the same results. But, well, it's not the same algorithm because I have not taken Harry Slaper's code and have, translated step by step each line. So the concept is the same. Come to the last point, comparison with another instrument. I think all of you know Quasume. Quasume was an EU-funded project in the beginning of the year 2002. It extended up to 2005. And after that, it became an operational program that is now hosted by our institute, PMOD. And we are traveling with this instrument around Europe and in the future also worldwide to provide quality assessment of UV spectra. Here is just a short summary of what we have done so far. We have visited more than 30 sites, more than 150 instruments. We have participated at all RBCC campaigns so far. And we have visited many of these sites more than once, which allows you also to see the long-term stability of your measurements. Now, this comparison is not that easy because the instruments will be different. I mentioned it in my first presentation. If the slit functions of instruments are different, and if you just take the ratio of two spectra, it will be really noisy. So you need a software like SCHC or MATSCHC to be able to bring it onto the same slit function resolution before you can then take the ratio of these two spectra. You do that for a couple of days, ideally clear sky so that it's very stable, but even under cloudy conditions you get some good results. And from that, you can then assess the quality of the measurements of the test instrument. Two more graphs and I'm finished. This is the example of the case that probably everyone expects from his instrument. You have a perfect agreement between the two instruments. On the top graph, you have spectral ratios over the whole day. You don't see any difference between the two instruments. The ratio is at 1, constant over the whole spectrum, and no diurnal variation. On the bottom, you see for individual wavelength the change over time during the whole day from 8 in the morning to 3 in the afternoon, very constant. With that one, you would be really happy. Usually we see different things. We see variabilities over time and over wavelength. In this case, you can see that the instrument has not a value around 1, but it's actually underestimating the UV by about 3 to 10%. It's changing during the day, and it agrees better in the UVB than in the visible or in the long UV range. So from that information, you, as an operator, would have to go back to your instrument and investigate where that problem comes from. This type of comparison will never be able to calibrate your instrument, because how should I produce a calibration from variable data like that? You could have a calibration at noon or in the afternoon. You actually should try to find out why your instrument is behaving that way, resolve it, and then you will have a better instrument. The conclusions from these two presentations: for reliable calibrations, you should be based on 1000-watt lamp systems, not only on 50-watt lamps, which represent only a relative calibration. Each instrument should be characterized individually. It's very seldom that a calibration or a characterization of one instrument can be disseminated to other instruments. This is quite unlikely. Typically, you would like to know its temperature correction, stray light, as you have seen. You should think about the linearity of your instrument, choose your right neutral density filter. There was this case of somebody from northern Norway coming to Greece for the comparison of spectroradiometers. His instrument was terribly nonlinear. in Greece. That's because he never had this type of conditions in northern Norway, so he was using the wrong neutral density filter. So these are things you have to consider when you have your instrument. And finally, comparisons to other instruments is the best way for evaluating your own data. Okay, thank you for your attention.